Hello, my name is Tomasz Jezak. Welcome to our project presentation for the AQA Academic Question Answering Model. Our goal is to provide the most relevant papers to best match technical questions. We use an OAG QA-derived training set, which includes questions and answers from Stack Exchange and a list of relevant papers. Our model learns to retrieve the top 20 most relevant papers to best answer the technical question. We evaluate our model using mean average precision and top K-map. The dense retrieval approach embeds documents into dense embeddings in a vector space, allowing us to retrieve relevant documents more effectively. Previous models for the AQA task include sparse models, which rely on exact term matching in a single vector space, which is less efficient and accurate. Dense passage retrieval, DPR, uses a dual encoder for queries and documents, creating two vector spaces. This approach is more effective as it can handle larger vocabularies and understands semantic similarity. The first significant step in DPR was fine-tuning BERT with contrastive learning to create accurate, dense embeddings. Contrastive learning is a technique that trains models by comparing and contrasting positive and negative examples. A later work, the Colbert model, was shown to be 2 orders of magnitude faster and use 4 orders of magnitude fewer flops per query due to its late interaction mechanism, which compares multiple vectors between queries and documents, making it scalable. Recent models, like supervised contrastive learning, have shown efficiency in unified contrastive learning for image text label pre-training, and we explore its use in text retrieval. Initially, we aim to compute the similarity of a question and paper abstract via inner product to produce a ranked list of top K relevant labels. In dense retrieval, traditional approaches use a single positive document per question with info NCE loss. However, our approach leverages multiple positive documents per question using SupCon loss, which has been shown to outperform info NCE in multimodal retrieval, though it hasn't been widely used for text retrieval yet.
So moving to methodology, let's first try to understand what we have in store for datasets. So we have 2 files. One is a QA train file, which is 8.7K Stack Exchange questions and the corresponding body text, and also annotated relevant papers. But if you see 8.7K documents is not a lot for training a dual encoder. But we are also in store this PID to title abstract.json file, which is an unannotated part of the project wherein the competition wants you to make full use of this. So that's why you break the training into 2 parts. For the first part, what we do is we try to do contrastive learning between the paper title and the abstract, and between the question and their text. So instead of using QA train.txt, which has annotated files, we simply learn a dual encoder to given a title of the paper, retrieve its abstract, or given the abstract, retrieve the title of the paper. And we add questions and their body text in here just for better training, because it's just more data and it's trying to do the same thing. So given that there is only one annotated text per query, like for every paper title or every question, we just have one abstract and body text, is why we simply use an info and CE loss. Basically, the SupCon loss reduced to the info and CE loss if you just have one positively annotated label or document for a query. So resulting, we get a dual encoder that, given a title of the abstract, can just retrieve the other. And we train a Distilbert model for this, and we use a sequence number 24 for the title of the paper or the question. And we use a 256 sequence length for the abstracts. And we train the model for 100 epochs with a batch size of 1500 on 4 NVIDIA A6000 GPUs. Each of these is a 48 GB GPU, 48 GB VRAM GPU. So for training process, like stage two, what we do is we now make use of the QA train.txt, wherein, and we again train dual encoder with the Q being a question and the body concatenated, and the abstracts being the title and the abstract concatenated. And we use a maximum sequence length of 384 for both Q and Z over here. And we train the model for 50 epochs with a batch size of 128 because of the increased sequence length, we can't fit in a bigger batch size. And we use two NVIDIA A6000s for this. Now for both, so for this stage, basically, we also use the ANS negative hard mining strategy, which basically is retrieving the top retrievals from the model itself while it's training using an NNS. So for example, every 5 epochs, we employ an NNS to get the top 5 retrievals for every training document for the model. And we use those as hard negatives to train the dual encoder while training. So for every Q that we sample, a question and the body, we have its positive type, which we have its positively annotated abstract, and two hard negatives that we sample from ants. And what we also do is we actually also use an interesting batching strategy, which comes from this paper Endgame. We have more details about this in the report, but the idea is to recursively cluster the query set using a two means hierarchical clustering unless you reach a cluster size, which is basically the size of the batch that you're looking for. So we get non-overlapping set of batches. So essentially every query is just once in the is just being trained on once in every epoch, just as before. But instead of using random batching, we just use this negative mining aware batching strategy, because what happens here is that the idea is that when you recursively cluster your query set, then the queries that end up getting in a batch, they are their positives serve as hard negatives for the other queries in the batch. And this is well proven, and this also works really well for our model.
Okay, so at a high level, what our model is doing is it's using its trained autoencoder to embed the title and abstract sections of each research paper. And from these embeddings, it constructs a graph using the HNSW algorithm, which allows us then to query the graph using the question and body text from the validation set, which is provided via this file that we're given. We use this validation set to query or retrieve the most relevant 20 papers. And we do experience a slight loss in accuracy because we're using an approximation as opposed to an exact search. But we'll discuss the motivation for that in the following slide. So the problem with an exact nearest neighbor search is it's far too computationally expensive for a problem of this magnitude. So the idea is we sacrifice a little bit of accuracy for a significant improvement in speed, which is why we use the ANNS algorithm. And then the advantage to using the HNSW algorithm, which is an advanced form of the ANNS, is we're able to construct this graph with various layers, where each layer represents a different granularity or grouping of points. And then we're able to logarithmically search over that graph, which allows for very efficient querying. So the way we apply it is, as I mentioned, we embed all of the title and abstract sections or we construct embeddings from all the title and abstract sections using our trained autoencoder. We create an ANNS graph, and then we query that graph using the validation set to obtain the top 20 most relevant papers for that query.
So next, we're going to talk about the results and findings from our model. In terms of results, we can independently analyze how each stage from our training impacted our final score given by the evaluation metric from the competition. When we ignore stage 1 and only train the model on stage 2, we get an evaluation score of 0.08499. We get a slightly higher score when we ignore stage 2 and only train the model on stage 1, where we get a score of 0.09919 on the validation set. However, when we use both stage 1 and stage 2 to train the model, we achieve a final score of 0.11902, which is our submitted score and ranks us 35th on the KDD leaderboard. Some more details on the specifics of our performance on the training data. So about 8% of the predictions had the ground truth paper as our top ranked paper. About 17% had the ground truth as a top 5 ranked paper in our model. And about 27% of our predictions had the ground truth paper within the top 20. We also have some example retrievals where our model performed well. with it correctly retrieving ground truth papers on within the top 5 for questions about Java and C++ and Spark's matrix multiplication. And as you can see in the third one, even though we did not predict one in the top 20 ranks, it still shows a common understanding of the question and a reasonable answer in our example.
Okay, so I just wanted to end off the results and findings section with some charts and visualizations. Here is a screenshot taken from the leaderboard website. You will see the Catalyst at rank 35 and Data Miner at rank 43. One side note is that our team name initially began as Data Miner, but it was changed to the Catalyst for more recent submissions, including our final submission. So sorry for any confusion that may have caused. But it does allow us to see our improvement. So this graph, at the top, you can see our early score with Data Miner at 9.0941, and our top final score with the Catalyst at 0.11902. The next two teams here are other easily identifiable CS145 teams, and their scores are hovering more around 0.06, which means that our score ended up being roughly 2 times these scores. And at the bottom of the chart, you will see the rank 1 and rank 2 teams from the website. I just wanted to clarify, I believe Black Pearl to be sort of an outlier. Their score is just far and away higher than anyone else's. Whereas RoboSpace gives you a better idea of the actual kind of clustering of top scores on the website. And then, of course, I feel like context is necessary. If you look at the amount of entries that these teams have had, Black Pearl has obviously been working on this for a while with 134 entries, RoboSpace with 48, and our 2 team names together have only had 13 total entries. So roughly half of the more reasonable top score is pretty good. Challenges and solutions. So obviously, when we're dealing with such a high, vast quantity amount of data like this project, efficient batch processing is of the utmost importance. And especially managing them to fit within the GPU memory can be quite a challenge. So in response, we implemented a hierarchical 2 means clustering system. Hard negative mining is another thing that we capitalized on. We dynamically mined them during training, and this led to our model being far more robust. We learned a lot of things from this project. First and foremost, the efficacy of supervised contrastive learning. We see that the SCL for dense retrieval tasks has better performance than the traditional methods. And of course, we were able to achieve better training efficiency and better model performance with those 2 things that I mentioned, the hierarchical clustering and the dynamic hard negative mining.
So in conclusion, there are several limitations with our model here, beginning with the small data set. Our training data set includes only 8,000 Stack Exchange questions and 350,000 paper abstracts. This relatively small size may be hindering the model's ability to generalize well to new unseen data. Larger and more diverse datasets could enhance both performance and robustness. Another limitation is the computational resources that's required. The model training process involves dual encoders in multiple stages, making it highly resource demanding, specifically requiring multiple NVIDIA GPUs. Such high resource requirements may restrict accessibility to using this model. In terms of impact and future implications, our approach using SUBCON loss presents a significant improvement over the standard InfoNCE loss, typically employed in similar models. SUBCON loss represents a significant step forward in dense retrieval. The success of SUBCON loss for text retrieval in our model suggests its broader applicability. This opens opportunities for its use in other domains, such as legal document retrieval, patent searches, or any text-heavy retrieval systems. There's also potential to integrate our model into academic research tools, such as academic search engines or digital libraries. Researchers will benefit from more relevant literature retrieval, potentially accelerating scientific discovery.